This is your presenter, Asloop Mudassar, and I am presenting slide number 3 of the course on atomic and molecular physics. The topics that will be covered in the today's presentation are Bohr's model for hydrogen-like atoms, incorporation of motion of nucleus in Bohr's atomic model, and structural and spectral lines of isotopes. These topics will be covered today. Bohr's model for hydrogen-like atoms. Neutral helium atom has atomic number Z is equal to 2 and lithium atom has atomic number Z is equal to 3. That is, there are 2 electrons in the helium atom and there are 3 electrons in the lithium atom. Hydrogen-like atoms are then helium singly ionized, because when the helium is singly ionized, then only 1 electron is left around the nucleus, and the lithium doubly ionized. So in the doubly ionized lithium, there is only 1 electron around the nucleus. So we can say that helium singly ionized and lithium doubly ionized ions behave like hydrogen atoms, and we regard them as hydrogen-like atoms. So all atoms which have only a single electron around a closed electronic shell or around a nucleus will be referred to as the hydrogen-like atoms. So following equation number 2.1 from the previous slide, the centrifugal force is given by Fc is equal to m0 Vn square over Rn. You see that here we are using the subscript n with velocity Vn and with the radius of the orbit as Rn. This n because in the previous slide we have found that the velocity and the radius and the orbital radius of the electron both are quantized quantities. That's why we have put a label n as a subscript with the velocity Vn and with the orbital radius of the electron as Rn. So substituting Vn by its value, which is Rn omega n, and finally the final result is the centrifugal force will be equal to m0 times Rn times the square of omega n, as shown in equation number 3.1. Now following equation number 2.2 from the previous slide, the Coulomb's force is given by Fc, here capital C stands for the Coulomb force, and the small c in equation number 3.1 stands for the centrifugal force. So here the Coulomb force is equal to 1 over 4 pi epsilon naught is times plus Ze times minus E, and plus Ze is actually the charge of the nucleus and minus E is the charge of the outer electrons, and then divided by the square of Rn. And this will be simplified as minus Ze square over 4 pi epsilon naught times Rn square, as shown in equation number 3.2. And you know that as we have used the concept of dynamic equilibrium from the previous slide, here we are also using the same concept that under dynamic equilibrium condition, the magnitudes of the two forces must be equal. So here we are equating, in equation number 3, we are equating the centrifugal force. We are equating the magnitude of the centrifugal force to the magnitude of the Coulomb force, which is shown in equation number 3.3. That is, an electron of charge E revolves around the nucleus of charge Ze in an orbit of radius Rn with a constant angular frequency omega n and a linear velocity Vn. So this is actually a brief description of the equation number 3.3. The orbital radius of the electron in the hydrogen atom was derived in equation number 2.20 of the previous slide, which is reproduced below. That is Rn is equal to, that is the quantized radius of the electron orbit Rn is equal to 4 pi epsilon naught times n square h bar square divided by m naught e square. And I have used the same label as 2.20. For a hydrogen-like atom, equation number 2.2 will take the following form. So Rn will be equal to 4 pi epsilon naught times n square h bar square and divided by m naught Z into E square. So you see that here I have introduced Z over here in the denominator because one charge, the E square charge in equation number 2.2. So one of the charge, one E plus one charge E is from the nucleus, the other charge E from the electron. So as far as the nucleus is concerned, I can use the charge ZE and the electronic charge as E. So the total charge, the multiplication of the charges becomes ZE square. So for a hydrogen-like atom, the equation, the orbital radius as shown in equation number 2.0 now takes the form as shown in figure number 3.4. That is, we have a dependence of Rn on the value of the atomic number Z of the hydrogen-like atom in the denominator. So Rn goes inversely with Z. Using Z is equal to 1 for the hydrogen atom, and n is equal to 1 for the ground state of the hydrogen atom, and using the data set given in equation number 3.4, that is this data set which I have shown below over here, the radius of the electron in the ground state of the hydrogen atom is. So you see that using the data which is given over here, that is m0 is the mass of the electron, which is equal to 9.1093837 into 10 to the power minus 31 kilogram. Reduced Planck's constant h bar is equal to 1.054571817 into 10 to the power minus 34 joule second. The electronic charge is equal to 1.60217663 into 10 to the power minus 19 coulomb, and epsilon naught is equal to 8.854 into 10 to the power minus 12 farad per meter. So using these values in the formula of equation number 3.4, we can find out the value of R1 as of the hydrogen atom is equal to A naught, denoting it this particular value by the value A naught is equal to 0.529 angstrom. So you see that this is the value of the first radius or the closest radius of the atomic hydrogen of the electron around the nucleus, which is given by R1, and we have denoted it with a particular symbol A naught. And this value you see that is 0.529 angstrom. Equation 3.4 can be generalized for the radius of the electron orbit when it is in the nth quantum state as given below. So you see that here you can separate out. For example, over here you can, in this formula, you can in equation number 3.4, you can separate in obtaining in order to obtain equation number 3.5, I have used n is equal to 1 in equation number 3.4. So for a general case, you can keep the value of n square as such, and you can the rest of the value will be the same as given in equation number 3.5. So we can write this as Rn, that is the radial, that is the orbital radius of the electron in the nth state of the hydrogen atom will be equal to n square times A naught, and that is equal to n square times the numerical value of A naught, which is equal to 0.529 angstrom. So you see that in equation number 3.6, you can put the value of any quantum state over here, and then you can find out the corresponding radius as given by equation number 3.6. Solving equation number 3.2 for the value of omega n square gives. So let me show you first the equation number 3.3. So you see that this is the equation number 3.3. You can solve this equation for the value of omega n square. And when you solve this equation for the value of omega n square, you will get omega n square is equal to 1 over 4 pi epsilon naught times z is square in the numerator divided by m naught r to the rn to the power 3 in the denominator. So this is equation number 3.7, giving you the value of omega n square. So you see that here we have used a subscript n with the omega, and because we have a subscript n with the r, so this rn is actually this rn takes acquires only the quantized value of the orbital radius of the electron. That's why so omega n will also be quantized. So whenever there will be a change of Rn by its discrete values, the omega n will also take discrete values. Using Rn from equation number 3.4, So let me show you equation number 3.4, which is this. So using the value of Rn from equation number 3.4 and substituting its value in equation number 3.7 gives. So you see that I have labeled Rn value by the color red, so that we can substitute the values of Rn over there, and over here below you can see that the value of omega n square is given by equal to 1 over 4 pi epsilon naught times z square over m naught, and this red value is actually the value of the 1 over Rn cube, and that is 1 over 4 pi epsilon naught raised to the power 3 multiplied by m naught z times e square divided by n square h bar square, this whole term raised to power 3. And this the value in the red is actually the value of Rn taken from equation number 3.4. So you see that after simplification of the values in this equation, you can finally get that Wn square is equal to 1 over 4 pi epsilon naught raised to the power 4, and then multiplied by a factor which has z to the power 4 e to the power 8 m naught to the power 2 divided by the cube of n square and h bar square. And you can also find out the value of omega n over here. That is taking the square root of both sides of this equation. You will get finally the value of omega n, which is equal to 1 over 4 pi epsilon naught raised to the power 2 multiplied by the term which contains z square e to the power 4 m naught divided by n cube and h bar cube. So this is shown in equation number 3.8, and the omega n is given by equation number 3.8. And here you can get the value, you can find out the value of omega 1, that is the value of the angular frequency corresponding to the first orbit of the electron around the hydrogen atom, which is equal to omega 1 of the hydrogen atom is nearly approximately equal to 10 to the power 16 hertz. And for that one you can substitute the values that I have given over here, the value of m naught, the value of reduced Planck's constant h bar, the value of the charge, the value of the epsilon naught, substituting these values over here, and the value of capital Z is equal to 1, you can find out the value of the angular frequency 1 as a function of the omega 1, that is the angular frequency corresponding to the first orbit of the electron around the hydrogen nucleus. So this is the angular frequency which is of the order of 10 to the power 16 hertz, and this is for the atomic hydrogen. In the first orbit of hydrogen corresponding to the ground state, the orbiting electron has the maximum angular frequency. Because the orbit is closest to the nucleus, it will have the highest value of the angular frequency. And when the electron moves away from the hydrogen, from the nucleus, that is, it attains other values of quantum number, that is, other higher states of the quantum values, then of course the angular frequency will decrease. According to the Bohr's atomic model, the electron is not radiating with this angular frequency omega n. Electron will radiate energy when it changes its quantum state. So whenever there will be a change of quantum state, then the atom will emit photons of a frequency omega n. And when the electron is moving in a fixed orbit, then of course the atom will not be radiating any frequency. So then what is the purpose? Then what is the meaning of this frequency that we have calculated omega 1 is of the order of 10 to the power 16 hertz? Then what is the meaning of this angular frequency if atom is not radiating any frequency when it is in a fixed orbit? If the electron is assumed to behave like a classical dipole in the atom, then omega n will be the classical frequency that the atom will radiate. So omega n as of the hydrogen atom will then be of the order of 10 to the power 16 divided by n cube. So you see that in obtaining W1 in equation number 3.9, we have used the value of n is equal to 1 for the first orbit of the hydrogen atom. But if you don't plug in the value of n and keep the value of n general over here and substituting the rest of the values, the rest parameters, the rest of the values of the parameters, then of course you will come out, then equation number 3.8 can be written as omega n, that is omega corresponding to the nth state of the electron in the hydrogen atom, will then be approximately equal to 10 to the power 16 divided by n cube, and this is in hertz. So you see that it is obvious that with higher value of n, then of course the angular frequency will decrease by a factor of n to the power 3. According to the Bohr's model, the electron will radiate according to the following equation. So you see that 3.10 will give you the frequency of the oscillations of the classical dipole of the in the atom. But you know that the atom will not be radiating any energy according to the Bohr's model. According to the Bohr's model, the electron will radiate only according to the condition given in equation number 3.11. That is omega is equal to 2 pi nu is equal to 2 pi and then multiplied by the factor which contains En minus En prime divided by h. The total energy of the electron in a hydrogen atom is given by, so capital E is equal to, this is the kinetic energy of the electron and this is the potential energy of the electron. So the kinetic energy is given by half m naught Vn square, and the potential energy of the electron is given by, which is due to electrostatic potential energy, is given by minus Ze square divided by 4 pi epsilon naught Rn, and this value is what we have calculated in the previous slide also. So you see that substituting Vn by Rn omega n, then we have this relationship. Since it is V square, so we have Rn square and omega n square in the first place from the first term, and then we have a minus Z square over 4 pi epsilon naught Rn. So 3.13 will give you the total energy or the total binding energy of the electron in a hydrogen atom. But this is not a hydrogen atom since it contains Z, so it means that this is the energy expression, or more accurately, this is the binding energy expression for the electron in a hydrogen-like atom. But if you put Z is equal to 1, then of course this relationship holds for the hydrogen atom. Otherwise, it will hold for the hydrogen-like atom depending upon the value of Z. Substituting omega n square from equation number 3.8 and Rn from equation 3.4 will give you. So let me show you the value of omega n square from 3.8. This is omega n square. This is omega n square from equation 3.8, and from equation number 3.4 you have the value of Rn. So now we are going to use these two values in this expression, that is in equation number 3.13, and you see that I have labeled their omega n square with the red font and then Rn with a green font, so that I can substitute the values and you can see. So in the first term I have half m naught Rn square shown in green, omega n square shown in red, and minus Z square over 4 pi epsilon naught, and again Rn is shown in red in green. So substituting the green value stands for the value of Rn and the red value stands for the value of omega n. So the first term has half m naught, then the green value is from the Rn square, and the other value, that is this value, is from the omega n square. And in the second term you can see that I have substituted the value of Rn, and here the Rn is in the denominator, and you will see that I have substituted the value of 1 over Rn in the second term in green color. So simplifying these equations, that is manipulating these parameters, I obtain this relationship that capital E is equal to half m naught and then 1 over 4 pi epsilon naught raised to power 2 and then Z square times E4 divided by n square and h bar square. And then the second term, from the second term we have a minus m naught 1 over 4 pi epsilon naught raised to the power 2 and then Z square times E4 divided by n square and h bar square. So you see that the two terms are exactly identical to each other, except that there is a factor of half with the first term. So half minus 1 will give you minus half. Then of course 3.14 gives you the final result of the binding energy for an electron in a hydrogen like atom. So this capital A on the left hand side is actually the binding energy of the electron in a hydrogen like atom, which is equal to minus half times m naught over 4 pi epsilon naught raised to power half raised to power 2 times the term which is z square e to the power 4 over h bar square, and then we have 1 over n square. So if I use z is equal to 1 for the hydrogen atom and n is equal to 1 for the ground state of the hydrogen atom, then of course I can find out the binding energy for the first orbit of the electron, which will be equal to E1 as E1 of the hydrogen atom. That is the energy corresponding to the first quantum state or the ground state of the hydrogen atom is equal to minus 13.59 electron volt. This negative energy indicates that this is the binding energy of the electron. So it means that if for such an electron, that is the electron in the first orbit of the electron, which is bound by this amount of energy, which is minus 13.59 electron volt, if you supply this much energy to the electron in the positive sense, if you supply this energy, that is, if you supply plus 13.59 electron volt to such an electron which is in the first orbit of the hydrogen atom, then the electron will be ionized. So this is the binding energy of the electron in the hydrogen atom when the orbit is closest to the nucleus. Also the ionization energy with the positive sign. For a hydrogen like atom in its ground state, now you see that now we are talking about the hydrogen like atom in its ground state, the electron binding energy is given by E1, which is the binding energy of the first orbit of the hydrogen like atom, is equal to z square times minus 13.59 electron volt. Because in the previous equation, that is in this equation given in equation number 14, I have not used the value of z over there, and the other parameters have been used numerically, and then I shall come out with this result which is shown in equation number 16. So E1, which is the energy, which is the binding energy of the electron in the first orbit of the hydrogen like atom, is equal to z square times minus 13.59 electron volt. And here z square, you see that you can because it is for the hydrogen atom, and you need to put the value of z if you are talking about the hydrogen, if you are talking about a particular case of the hydrogen atom. And here I am using z H with a subscript Z, which means that this is a hydrogen-like atom, but Z means that it is a hydrogen-like atom for which you have. If you put Z is equal to 1, then of course it becomes a hydrogen atom. And if you use other values of Z, then of course that will be the case of the hydrogen-like atom. And you know that the basic energy of the basic energy, which is the energy corresponding, which is the binding energy corresponding to the first orbit of the electron in the hydrogen atom, is multiplied by z square for the case of a hydrogen like atom for the same orbit, that is for the first orbit. For a hydrogen like atom in its nth state, now suppose that the hydrogen atom like atom is not in the ground state, but is in but suppose that it is in the nth state, then the electron binding energy can be written as En, that is the energy in the nth state of a Hz mean of a hydrogen like atom having atomic number Z, will be equal to Z square divided by N square times minus 13.59 electron volt. So you see that for a hydrogen-like atom, you can calculate the binding energy of any electron in the nth state of such a hydrogen-like atom. Let's compute the wave numbers represented by nu bar using the binding energy formula given in equation number 3.14. That is this. So this is the energy expression, and we can use this energy expression in order to calculate the wave number corresponding to the desired case. Let's now compute the wave number nu bar using the binding energy formula given in equation number 3.14. and the empirical formula suggested by Bohr for the data fitting of the spectral data of hydrogen atom. So you see that this nu bar, which is equal to 1 over hc multiplied by En minus En prime. So using the values of En, using from equation number 3.14, which is given over here. So using the value, because this, you know that this E actually depends upon the value of n square. So using this value over here, you can get the value of nu bar is equal to 1 over hc is equal to half times m naught over 4 pi epsilon naught raised to power 2 multiplied by the factor which has z square e to the power 4 in the numerator and divided by h bar square in the denominator, and then multiplied by minus 1 over n square plus 1 over n prime square. So rearranging the parameters, then you have nu bar is equal to 1 over 2 pi multiplied by c, and then you have a half multiplied by m naught over 4 pi epsilon naught raised to power 2, and then you have a factor which has z square e to the power 4 divided by the cube of h bar, and then parenthesis contains 1 over n bar square minus n square minus 1 over n square. So this is the full expression of the nu bar for a hydrogen like atom because it contains the value of z. And you know that you have these two numbers, quantum numbers also. So it means that when there will be a change of quantum state from n to the n prime, then of course the nu bar will be equal to this expression. And if you are using a hydrogen like atom with an atomic number z, so using appropriate values, you can calculate the corresponding value of the of the wave number. So you see that I have I have labeled this equation by 3.18 and I have rearranged the terms over here. So nu bar is equal to, you can compare this with the last equation and you can see that I have rearranged the terms in the previous expression to obtain the present expression given in equation number 3.18, giving a full expression for the wave number. And you know that this is the wave number corresponding to the case of the hydrogen-like atom. The empirical formula suggested by the Bohr is now given. So you see that this expression, which is given in equation number 3.18, is obtained according to the model of according to the Bohr's atomic model. But you know that we have a similar expression of the wave number given by the Bohr, which gives you, so the empirical formula suggested by the Bohr is now given, which is nu bar is equal to RH, which is the Rydberg constant, times 1 over n prime square minus 1 over n square. And you see that here R, you can use RH or you can use the value of R from equation number 2.16. I have mentioned this value for the first time in equation number 2.16, and this equation was the result of the using semi-classical theory. So you see that let's represent R in appropriate form. This R which is given over here, I am using appropriate form of this equation. So I am going to convert h cube into the h prime cube. So I am reducing a reduced Planck constant. So for that one, I am dividing h over 2 pi, which is shown in the red, and then I have multiplied the denominator by a factor of 2 pi raised to the power 3, so that I can write h as h bar. And then you see that the final result on the right hand side gives you 1 over 4 pi epsilon naught raised to the power 2, and then the factor which has m naught divided by 4 pi c, and then another factor which is e to the power 4 divided by h bar cube. So equation number 3.20 gives you the value of R in appropriate form. So we can use this value of R in the form at the position of the Rydberg constant. So this expression, so using equation 3.20, the equation 3.19 then takes the following form. So this nu bar is equal to 1 over 4 pi epsilon naught raised to power 2 multiplied by a factor containing m naught over 4 pi c multiplied by a factor which is e to the power 4 divided by h bar cube multiplied by the parenthesis containing 1 over n bar square minus 1 over n square, as shown in equation 3.21. Now we have two equations. One is 3.21, which is due to the numerical formula given by the Bohr series, which explains the Bohr series, and this is the appropriate form of that formula. And the other one, which is shown in equation number 3.18, was obtained using the Bohr's atomic model. So you can compare the two results over here, which are quite consistent with each other and exactly the same relationships. So 3.18 and 3.2 and 3.21 are exactly the same. So comparison of equation number 3.18 with the equation number 3.21 reveals that the wave number expression derived for the hydrogen-like atom for Z is equal to 1 is identical to that of the empirical formula of the Bohr suggested for hydrogen atom. So you see that this expression, the previous expression, this expression was written for the hydrogen-like atom as given in equation number 3.18 because it contains the value of Z, whereas the formula which is given in equation number 3.21 is for the hydrogen atom. And you see that the two formulas will hold when you put the value of Z is equal to 1 in equation number 3.18. And the formula given in 3.2 is the empirical formula of the Bohr suggested for hydrogen atom. And this formula, which is in 3.18, is for the hydrogen-like atoms. So this is the wave number that you can compute for the hydrogen-like atoms. The empirically found Rydberg formula, that is equation number 3.19. Let me show you. This is 3.19. The empirical found Rydberg formula given in equation number 3.19 shows complete agreement with respect to quantum numbers n and n prime. The empirically found Rydberg formula 3.19 shows complete agreement with respect to the quantum numbers n and n prime. You see that in the formula which was suggested by the Bohr as an empirical formula and also known as the Rydberg formula, that in that formula n and n prime were just ordinary indices, only integer values. But here you see that in equation number 3.18 we have found that n prime and n due to the Bohr's atomic model are actually the quantum numbers corresponding to the quantum state n prime and n. So that's why we can identify over here these n and n prime as the quantum numbers. But when it was suggested by the Bohr for the as an empirical formula, also known as the Rydberg formula, at that time n and n prime were not identified as quantum numbers but just as integers. Bohr introduced quantum numbers n, which is also identical with the index n of the Bohr formula. So now we can identify that in the Bohr formula, the indices n and n prime are actually the quantum numbers n and n prime suggested by the Bohr's atomic model. Now you see that now we are going to talk about the motion of the nucleus. Why we need to talk about the motion of the nucleus? Let's see. You see that this is the value of RH, that is the value of the Rydberg constant, which is equal to 4 over capital G. And its value is 109677.5810 centimeter inverse. So this was first mentioned in the previous slide at equation number 19. So this is equation number 2.19. So this was the empirical formula that was suggested, that this is the empirical value of the RH value that was suggested by the Bohr in order to satisfy the spectroscopic data obtained in connection with the Bohr series. And the other formula, which is R value, obtained using the Bohr's atomic model, is R is equal to R infinity, because R infinity means that this also is relevant to the ionization energy of the hydrogen atom of the first electron of the hydrogen atom. That is why we have used R infinity as the term which was introduced in slide number 2. So that's why I am also using R infinity over here, so that you can identify that this is the same number. So here now instead of R infinity, I am using the capital letter R. So this value of R is equal to, as mentioned also in the previous slide, at equation number 18 is 109737.318 with the tolerances of 0.012 centimeter inverse. So these two equations were mentioned in the previous slide as equation number 19 and equation number 18 respectively. So equation number 2.18 was obtained from equation number 2.16, or equivalently from equation number 3.20, which is reproduced below. So you see that this equation, which is equation number 2.18, was obtained from this equation number 2.16, which was modified in an appropriate form as given in equation number 3.20. Equation number 2.16 is the same as equation number 3.20, except the difference is only is that equation number 3.20 is written in a more refined and useful form. So both equations are the same. So the data presented in equation number 2.18 was actually obtained from equation number 3.20 or from equation number 2.16, as both equations are identical. But you know that there is a difference between the two values. The RH value given in equation number 2.19 was suggested as an empirical value by the Bohr in order to satisfy the Bohr series. But you know that this value of R as given in equation number 2.18 was obtained using semi-classical approach, and you see that this was also obtained numerically using equation number 2.16 or equation number 3.20. So both the above results are identical. RH is due to Bohr and capital R is due to Bohr or due to semi-classical approach. And you know that there is also a small difference between them. The question is that why these two values are not exactly the same? Where is the problem? So we shall find, since RH value given in equation number 2.19 completely satisfies the statistical data obtained from the Bohr series. So it means that this RH value satisfies fully the experimental data. So we assume that RH value is an absolutely correct value. Then what is the problem with the value of R given in equation number 2.18 or obtained through semi-classical approach? So let's find out. Equation number 2.19. So let's discuss these two. Equation number 2.19 was obtained from the analysis of spectroscopic data by Bohr, whereas equation number 2.18 was obtained theoretically under Bohr's atomic model or using semi-classical approach. So let me take the difference of these two quantities. That is the difference of R minus RH. So that we can see the magnitude of the difference between the two values. So if you take R infinity minus RH, or simply R minus RH, you will see that it is of the order of 60 centimeter inverse. The reason for this difference is that the motion of the nucleus was neglected by the Bohr's model, and only the electron motion was considered. So you see that this is why the reason we need to consider the nuclear motion in order to derive a modified formula. So if the nucleus is treated as an infinitely massive object, then it could be treated as stationary with respect to the electron. This was assumed in the Bohr's atomic model. So you see that in the Bohr's atomic model, it was assumed that the nucleus is so massive with respect to the electron that the motion of the electron around the nucleus will not affect the motion of the nucleus, and the nucleus will be treated as a stationary particle. But you see that this was not the case. So in reality, the mass of the nucleus is finite. So we need to consider the mass of the nucleus because the nucleus could also be displaced while the electron revolves around the nucleus. So in order to incorporate that is the motion of the nucleus, we are assuming that the mass of the nucleus is not infinite but finite. And this picture on the left hand side shows two masses, M1 and M2. You may consider M2 as the mass of the electron and M1 as the mass of the nucleus. And Cg is the center of gravity. And capital R, small r is actually the separation of the electron from the center of the nucleus. That is, R defines the orbit of the electron. So electron revolves around the mass M1 or the nucleus M1. And this picture can be expressed in terms of the reduced coordinate. In the reduced coordinate system, we have a mass which is mu moving around a fixed center of gravity. Then you see that center of gravity is just a point, it is not a mass. So this center of gravity is a fixed point, and only a single mass mu revolves around the center of gravity with a fixed radius r. And Cg is fixed, so the center of gravity is no more moving, and this is the reduced mass of the problem. So what is mu? M1 and M2 are two masses in motion separated by a distance r with common center of gravity Cg, also the Cg of the motion. The situation shown can be treated as a single mass mu in motion, because we are now representing the single mass in motion, which is represented by the mass mu around a fixed center of gravity Cg. So the situation shown in the second figure can be treated as a single mass mu in motion at a distance r from a fixed center of gravity Cg. The mass mu is called reduced mass and is given by mu is equal to m1 times m2 divided by m1 plus m2. Okay, now we can replace m1 with the mass of the nucleus. So if capital M is the mass of the nucleus and m0 is the mass of the electron, then the reduced mass of the problem is given by mu is equal to capital M times m0 over capital M plus m0. So in equation number 221, we have replaced m1 by the mass of the nucleus and we have replaced m2 by the mass of the electron. So the reduced mass of the problem of an atomic problem containing the mass m of the nucleus and mass m0 of the electron will produce, will effectively give you the reduced mass of the system, which is represented by mu. So RH gives the correct value, as I have suggested. Since RH, the Rydberg constant, was introduced by Bohr in order to explain the spectroscopic data, especially spectroscopic data concerned with the Bohr series formula, and RH was proposed, which was equal to 4 over G. Since this satisfied the spectroscopic data or the Bohr series data, so we assume this RH satisfying the experimental data very precisely to be as the precise data. So RH is a precise value. So you see that here we are mentioning that RH gives a correct value, whereas the correction is required in the value of R by taking into account the nuclear motion, that is the mass of the electron m0 in equation number 3.20 should be replaced by mu, giving R as RC. So RC, so R, so when we replace m0, that is the mass of the electron, by mu, then the value of R can be replaced by RC, and RC stands for the corrected value of R. So C subscript C stands for the correct and RC stands for the corrected value of R. So you see that this value of R now needs a correction, and it means that equation 3.20 needs a correction over here. And what we need to do is that if you replace m0 with the value mu, then this R will be referred to as RC. That is the corrected value of the R value. So you see that RC will be equal to 1 over 4 pi epsilon naught raised to power 2 multiplied by mu. You see that here I have replaced the value of m0 by the value mu. The rest of the quantities are the same. Mu divided by 4 pi c and then multiplied by a factor which contains e to the power 4 divided by h cube. And you see that now I am going to plug in the value of m, plugging the value of mu, which is equal to m naught, which is equal to, as you can see in equation number double two, that mu is equal to m times m naught over capital M plus m naught. So I am using m naught over here at its original position, and the rest of the term is written on the right hand side, which is equal to capital M divided by capital M plus m naught. So you see that this value which lies in the middle, which is shown in the red in the next step, is actually the value is equal to R value. So this actually the R value which was given in equation number 3.20. So this is the R value which is shown in the red in over here, and this will be replaced by its capital value R. And then the other term which is equal to 1 over 1 plus m naught over capital M, because I have divided the numerator and the denominator by the total value capital M. So this is the corrected value of RC, that is the corrected value of R is equal to the value of R multiplied by this factor, which is 1 plus m naught over capital M, as shown in equation number 3.2. So this factor is actually, we can say that the correction term is equal to 1 over 1 plus m naught divided by capital M. So this is the term that we need to multiply with the value of capital R in order to obtain the correction, or in order to obtain the corrected term represented by RC, written on the left hand side of equation 3.23. So RC in equation 3.23 is now identical to RH. That is RC is equal to RH value. That is RC will be the same as the RH value. So equation 3.23 can now be written as, so this value is RH, which is the same value as RC, but now this is equal to, because now we have introduced there the correction. So that's why this value is RH, because RC is now RH, because both will be equal to, both are the same things. So I have replaced RC by RH, and then RH is equal to R times over 1 plus m naught over capital M. So it means that this RH on the left hand side, you can say that this is the value that after obtained after correction, or you can say that this is the value of given, this is the value given by the Balmer series formula, or the empirical value proposed by the Balmer, and this R is the actually the value obtained by Bohr, and this is the correction due to the motion of the nucleus was incorporated in equation number 3.23. So you see that under this condition, the both values will be equal to the same, that is the values RH and this value R would be same if you multiply this value with the correction factor, which was so second value in equation number 2.18 must be multiplied with the correction value, and the correction term was equal to 1 over 1 plus m naught over capital M, where m naught is the mass of the electron and capital M is the mass of the nucleus. So you see that equation number 3.23 can now be written as m naught over capital M is equal to capital R over RH minus 1. Or more accurately, if you take the reciprocal of this equation, you will get capital M divided by m naught is equal to RH over R minus RH. So you see that now this R is RH. You see that this R is the value over here, the numerical value of R, which is shown in red, which is shown in green in the equation I have just shown you. So this value is the R value, and this is the value of the RH shown in red in the equation. So using those numerical values over here, which is shown over here, so capital M over m naught is equal to this value 109677.5810 centimeter inverse divided by the value of R shown in green 109737.318 minus again the red value of RH, which is 109677.5810. So if you take the difference in the denominator and divide it to the divide the numerator by the denominator difference, you will get this value, which is equal to 1836.007. And you know that this is well known, the ratio of the mass of the nucleus to the mass of the electron in a hydrogen atom. This is since in a hydrogen atom the mass of the nucleus is equal to the mass of the proton, so you can say that this is the ratio of the mass of the proton to the mass of the electron, which is well known, well documented quantity, and this is 1836.007. This is how the ratio of the mass of the nucleus to the mass of the electron can be determined in a specific problem using spectroscopic data. So you see that we have used the spectroscopic data in order to evaluate the ratio of the mass of the proton or the mass of the nucleus of the hydrogen atom to the mass of the electron. So let's evaluate these values with the real data. So mass of the proton is equal to 1.67 into 10 to the power minus 27 kilogram, and the mass of the electron is 9.1093837 into 10 to the power minus 31 kilogram. So if you take the ratio of these two masses, you will get 1836.15. So this is very close to this data, because we have not included tolerances in the green value that I have presented over here. So, and these MP and M0 are the rest masses of the proton and the electron. So you see that here we have discussed that this is the important term for the correction of the values of the R with respect which reduces the difference between R and R to its nil value. That is okay. Now let's move to the next case, which is the spectral lines of isotopes. Different isotopes of the same element of hydrogen, like atoms, have slightly displaced spectral lines. In the emission spectrum of hydrogen atom, each spectral line was found to be doubled and with equal intensities, because the mixture contained equal number of hydrogen and the deuterium atoms. You see that hydrogen contains one proton only, and the deuterium contains one proton plus one neutron. So here the mass of the deuterium is different. Mass of the nucleus of the deuterium atom is different from that of the hydrogen atom because of the inclusion of the one proton there. So I am going to show you the emission spectrum of the first two lines of the first lines of the Bohr series. So H beta is actually the first line of the Bohr series of the hydrogen, of the atomic hydrogen, and D beta is also the same line due to the presence of the deuterium atom there. You will see that there is a difference that in the emission spectrum you will observe the two lines side by side. So one line is the H beta line, the other one is the D beta line. And you see that this H beta line is actually the transition of the probably the first line of the Balmer series of the hydrogen atom, due to the hydrogen atom H beta, and due to the deuterium atom is D beta. And the separation between these two lines is 1 angstrom. So if you take the emission spectrum of the specimen which contains hydrogen and deuterium atom in almost equal number, you will observe the two lines in the emission spectrum. One corresponds only when you are talking about the Bohr series, and then of course you can observe different lines in the series. But if you talk the H beta and D beta lines of the Bohr series, then of course you will notice that the two lines in the emission spectrum will be separated narrowly by one angstrom apart. and this is of course due to the change in the nuclear mass of the deuterium with respect to that of the hydrogen atom. There was a measurable difference in the corresponding lines of the hydrogen and deuterium Lyman series. So now I am talking about the Lyman series, giving you the spectrum of the hydrogen atom and the deuterium atom. So R, the corrected value of C, this is the corrected value of R. C stands for the corrected value. So RC means corrected value of R, which we have discussed earlier, due to the hydrogen atom is equal to R times 1 over 1 plus m naught over mh. And mh is the mass of the hydrogen atom, and its value is this, which is equal to 109677.584 centimeter inverse. And the second line contains RCD, which is the corrected value of R for the deuterium atom. And this will be equal to R times 1 over 1 plus m naught over md, where md is the mass of the deuterium containing 1 proton and 1 neutron. So if you specify these values over here, you will get the value of Rc, that is the corrected value of R for the deuterium atom will be equal to 109707.419 centimeter inverse. So you can use these two values in the Lyman series formula, and delta lambda, that is the difference between the wavelengths due to the hydrogen atom and the deuterium atom, will be equal to lambda h minus lambda d. So if you take lambda h common from this one, you will get lambda h multiplied by the parenthesis containing 1 minus lambda d or lambda h. And here you can, rather than manipulating the wavelengths, you can introduce wave numbers over there. Since wave numbers are reciprocals to the wavelengths, so you have equal to lambda h multiplied by the parenthesis containing, in terms of wave numbers, we have 1 minus nu bar due to hydrogen divided by nu bar due to deuterium. And if you plug in their values in terms of the wave numbers using the Bohr series formula for the Lyman series, you have the parenthesis which contains 1 minus corrected value of Rc for the hydrogen atom multiplied by the parenthesis, which shows you 1 over 1 square minus 1 over n square for the Bohr series for the transition from the state n to the state 1, because you know that in the Lyman series, the first state has all the transitions will be to the ground state of the atom, where the principal quantum number has a value n prime has a value equal to 1. And similarly for the deuterium atom, we are also using the transition for the Lyman series, that is to the first state of the, that is to the ground state of the deuterium atom, which have the principal quantum number n prime is equal to 1. So RCD, the corrected value for the deuterium atom multiplied by 1 over 1 square minus 1 over n square. So you see that the terms read in the numerator and the denominator will be cancelled out, and then you have delta lambda, which is equal to lambda h multiplied by 1 minus RH over RD. Or more precisely, the corrected value of RH divided by the corrected value of RD. So it means that putting these corrected values, you will notice that delta lambda will be a constant quantity for as far as the Lyman series is concerned. So let me show you the comparison of lines of the Lyman series formula obtained experimentally. So lambda d shown in angstrom on the left column, and lambda h for the hydrogen atom shown in angstrom on the right hand side. So for the deuterium atom, you will notice that the first line of the Lyman series was 1215.31, whereas the same line for the hydrogen atom under the same transition was equal to 1215.66. The second Lyman series experimental data gives you 1025.42 angstrom, and the same line for the hydrogen atom gives you 1025.72 angstrom. The third line of the Lyman series obtained experimentally gives you for the deuterium atom as 972.25 angstrom, and for the hydrogen atom obtained experimentally between the third line from the Lyman series will give you 972.53 angstrom. You will notice that the difference of these two quantities is constant. And if you put the value of RH over RCH over RCD in this formula of delta lambda, you will see that this will explain, this will be a constant number, and this constant number is verified by the experimental data of the difference of these two quantities. So you see that I have explained in the today's lecture these topics, and the topics were that I have explained the Bohr's atomic model for hydrogen-like atoms. I have incorporated the motion of the nucleus in the Bohr's atomic model, so that I can explain the discrepancy between the values of the Rydberg constant and the expression that we obtained using semi-classical approach as a counterpart of the Rydberg constant. And the second, the other thing that I have explained is the spectral lines of the isotopes. The difference was there, the difference between the wavelengths emitted by the different isotopes of the hydrogen atom was also explained, and the theory was generalized for the hydrogen-like atoms. So you see that this is the end of slide number 3 of the course on atomic and molecular physics.